In this video, I am introducing the standard minimization problem. To do a standard minimization problem, we first need to understand what a standard minimization problem looks like. So, a standard linear programming problem is a problem that is either a standard maximization problem, which we've already looked at, or a standard minimization problem. An LP problem satisfies the non-negative objective condition if all the coefficients in the objective function are non-negative. So let's take a look at that. Here is the first example, and it says minimize C equals 2S plus 3T plus 3U. Notice that all the terms in that objective function are positive, so it satisfies the non-negative objective condition. Standard minimization problem is an LP problem in which we are required to minimize the objective function. So we are being asked to minimize. So both of these conditions are met. It's a minimization problem and it satisfies the non-negative objective condition. But what else makes it a standard minimization problem is the fact that all of these inequality signs are greater than or equal to. Remember, with the standard maximization problem, they all were less than or equal to. Now they have to be greater than or equal to. So this is a standard minimization problem. All of the objective function terms are positive. We are being asked to minimize, and all of the inequalities are greater than or equal to. In the second example, we are being asked to maximize, and it says P equals 2x plus 3y plus 3z, and all of the inequalities are less than or equal to. And of course, we don't worry about the non-negativity restraints. So this is a standard maximization problem. In the third example, minimize C equals 2S minus 3T plus 3U. This does not meet the non-negativity requirement for the objective function, even though the inequality symbols are all greater than or equal to. So this is a standard minimization problem, does not satisfy the non-negative objective function. So those are two different things we want to be looking at when we're doing our problems. Next, we're going to take a look at this idea of duality. If you have two linear programming problems, one is a maximum and one is a minimization problem, and they are dual if the matrix that represents one is the transpose of the matrix that represents the other. So basically what we're going to be doing is we're going to be starting with a standard minimization problem, and we are going to be creating the dual problem, and that dual problem will be a standard maximization problem. So we're going from a standard min problem, creating the dual, and ending up with a standard maximization problem. And so these are the basic steps, which I will be going over. Represent the problem as a matrix. So we know how to do that. Take the transpose of the matrix. Write down the dual, which is the linear programming problem corresponding to the new matrix. If the original problem was a maximization problem, its dual will be a minimization problem, and vice versa. The original problem is called the primal problem, and the dual is referred to as the dual problem. Now here's the really important idea. If a linear programming problem has an optimal solution, then so does its dual. Moreover, the primal problem and the dual problem will have the same optimal value for their objective function. So we're going to start with a standard minimization problem, create a dual problem, which will be a standard maximization problem. That standard maximization problem will have an optimal solution, and it will be exactly the same as the solution to the standard minimization problem. So let's take a quick look at the first example. Here is our original linear programming problem, and we can confirm that it does meet the non-negative objective function and it is a standard minimization problem. All the inequalities are greater than or equal to. So what we want to do is create a standard maximization problem. We do that by first creating a matrix. Now, to create the matrix, we start with the first inequality. And so the coefficients of S and T are 2, 1, and the constant is 20. So 2, 1, 20. This would be our S column. This is the T column and the constant column. Second inequality, 1, 2, and 20. 1, 2, and 20. 3, 4, 50. 3, 4, 50. And then on the bottom is the objective function. The S is 2,000, 3,000 T, so 2,000 goes in the S column, 3,000 in the T column, and then 0 in the constant column. So that is our matrix. Now, to create the dual, we take the transpose of that matrix, which we learned in the unit on linear algebra. So remember, to find transpose, we simply switch the rows and the columns. So row number 1, 2, 1, 20, becomes column number 1, 2, 1, 20. Row number 2, 1, 2, 20, becomes column number 2, 1, 2, 20. Row 3, 3, 4, 50, column 3, 3, 4, 50. And finally, the bottom row, 2,000, 3,000, 0, becomes the last column, 2,000, 3,000, 0. Now from there, we actually create the dual problem. So the bottom row, remember, just like up here, will always be associated with the objective function. So remember, we're going from a standard min to a standard maximum problem. So we want to write this as P, maximize P equals 20x, 20y, 50z. And that's our objective function. We don't really need to do anything with that 0. Then these first two rows become our new constraints. So our first constraint is 2x plus y plus 3z, 2, 1, and 3. And so because it's a standard maximization problem, we have less than or equal to 2,000. And then we have 1x, 2y, 4z is less than or equal to 3,000. One last thing to notice about this is it's nice when we write the original primal problem to use what we would normally use as slack variables, like R, S, T, U. In this particular case, it was S and T. And in the dual problem, the standard max problem that we created, we use the traditional variables, X, Y, Z, W. Also notice that in the original problem, we had 2 variables and 3 constraints. But in the dual problem, we have 3 variables, 2 constraints. That will always switch. However many variables you have here, that will be the number of constraints that you have. The number of constraints you have will be the number of variables. So the number of variables and constraints always switch when you do the transpose. All right, once you have the new standard maximization problem, you solve that problem just like we learned how to do when solving standard maximization problems. You'll create your initial table, you'll look for your pivot, you will clear the columns until you get to the point where you have a table where the bottom row is all positive numbers and zeros. Okay, so this took 2 tables, and I'm not going to go through all the steps there, but what I do want to go through is how we determine the solution. It's a little bit different. To determine the solution, now we're really looking for the solution to the original primal problem, which the variables are S and T. So in our final table, what we're going to do is we go to the S column, and we look for the bottom number in the bottom row, which I've highlighted, is 30. Then we go to the T column, and we go to the number on the bottom row, 15. Same thing with P, go to the bottom row, and the constants. So I've highlighted these numbers because those are the numbers that we need. Now, To find the solution to S in the original problem, we want to know what S is. So to find S, we take this value right here, 30, and divide it by the p-value, 3. 30 divided by 3 is S equals 10. To find the value of T, we take 15 divided by 3. 15 divided by 3 is 5. And finally, to find the value of P, 105,000 divided by the p-value, 3, is 35,000. Now, 105,000 is the optimal value. That's the solution to both the dual problem and the primal problem. So 105,000 divided by 3, 35,000 rather, is the solution to the dual problem and the primal problem. So standard minimization problems are similar to standard max except at the beginning and the end. At the beginning, we have to find the dual by finding a transpose, and then everything else is the same until we get to the final table. And so finding the values of the variables in the final table are a little bit different. All right, I'm going to make a couple of other videos. One video is going to be just about creating the dual, and the other video is going to be just about interpreting the final table to find the solutions. So I hope you found this helpful. Have a good day.